All right, so we're going to go ahead and start chapter 4, which is going to deal with some rules that we have for taking the derivative of a function. And derivatives are super, super important in calculus. Not only are we going to talk about how to take the derivative of a function, but we'll also look at like what the derivative tells us, and then how we can use derivatives to determine some important things regarding functions. So today's lesson is going to be really lengthy because I'm kind of like combining like 2 sections worth of stuff in a single lesson. So we're going to take a look at the derivative and the tangent line problem. Now, the technique that we use for finding a derivative in this section is really lengthy, is really time consuming. We're going to learn like faster techniques to take derivatives down the line. But for the time being, like we need to work through these derivatives in this longer way. It's going to make you appreciate the shorter ways of taking derivatives later on. And believe me, no one is more unhappy about this than I am, because I have a pretty good foundation of algebra. So these derivatives take a long time to work through, but we're all going to work through them together. And again, it's going to help you like with your algebra skills when it comes to simplifying expressions, which is something that you're going to need once you start taking derivatives of complicated functions. Okay, so the first thing we want to get into is what's called the average rate of change. So it says the average rate of change of the function f on the closed interval from a to b is the slope of the secant line containing the endpoints. Okay, so if we have some curve, which we have here, y is equal to f of x, we've identified 2 points on the graph of that curve. Okay, we have the point P, which has coordinates a comma f of a, and then we have the point Q, which has coordinates b comma f of b. Okay, so if we want to calculate the average rate of change, what we want to do is we want to find the slope of the segment that contains those 2 points. So I'm going to go ahead and draw that segment there, or that line in red. So we want to calculate the slope of the line or the slope of the segment that contains those 2 points. So what do we know about slope? Well, we know slope is the ratio of the rise over the run. So the rise refers to the change in y coordinates, which is going to be f of b minus f of a. And then we're dividing that by the run, which describes the change in the x direction or the change in x coordinates, which is going to be b minus a. Okay, so if we want to calculate average rate of change, that's just essentially asking us to find the slope of the line that contains the 2 endpoints of that interval. And as we mentioned down below here, to calculate average rate of change, you need 2 points on an interval. Okay, so you might have seen average rate of change before in math class, but the next thing we're going to look at, instantaneous rate of change, is going to be a brand new idea. Okay, that's what calculus is all about. Okay, so the instantaneous rate of change of the function f at the point x is equal to a is the slope of the line tangent to f at x is equal to a. All right, so again, the instantaneous rate of change of the function f at the point x is equal to a is the slope of the line tangent to f at x is equal to a. And this can be found in 2 ways. Okay, so the slope of the tangent line, we're going to take a look like later on in this lesson. So the slope of the tangent line, this instantaneous rate of change, in calculus we use a derivative to describe that. And one of the ways that we can denote a derivative is by taking f prime at some number a. Okay, so f prime indicates or denotes a derivative in calculus. And like I said, we're going to talk more about that later on in this lesson. Okay, so the first way that we can calculate the slope of the tangent line, or f prime at a, is to take the limit as x approaches a of f of x minus f of a all over x minus a. Okay, so I want to talk about how this formula calculates the slope of the tangent line. Okay, so what the tangent line is going to look like, the tangent line at A is going to be this line in green here. Okay, so it's going to be a line that touches our curve at that one point at x is equal to a. Okay, well, if we look at this expression that we have here, f of x minus f of a over x minus a. Okay, what we said up above in regards to average rate of change is that formula right there is going to calculate the average rate of change of the function on the interval from a to x. Well, when we take the limit as x approaches a, what we're going to do is we're going to take this point here at x comma f of x, and we're going to move that point at x comma f of x really close to the point at a comma f of a. And when you compare these slopes right now, the slope in green is not close to the slope in red. Those two slopes are completely different. Okay, but if I take that point at x comma f of x and move it really close to the point a comma f of a, so I'm going to go ahead and move the point x comma f of x close by that point, drawing that in light blue. Then if I draw the secant line passing through these 2 points here, if I connect the dot in blue to the dot in green, like those two dots are going to give me something that is going to wind up being the slope of the tangent line. So if I move those 2 points really close together, the slope of the secant line becomes the slope of the tangent line. Okay, now to be honest, I very rarely use that limit definition to calculate the slope of the tangent line. There's only like one type of function that I'm going to use that for, and we'll take a look at that later on in this lesson as well. Okay, the one that I like using more commonly is the second limit definition, where the slope of the tangent line, or f prime of a, is going to be equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. Okay, so I want to look at this expression here in more detail. Okay, if I calculate the slope of the secant line that passes through those 2 points, the formula that's going to calculate that for me is f of a plus h minus f of a. So that's the difference in my two y coordinates, okay, f of a plus h minus f of a, all over the run, which is the difference in between the two x coordinates, which is going to be a plus h minus a. And when you look at that denominator, a plus h minus a, the positive a and negative a cancel one another out. So that just makes our denominator h. Okay, so this formula here, this one right here, calculates the slope of the secant line that passes through the 2 points on our graph. Okay, now just like we had before, if I want to draw the line tangent to our graph at A, That would be this line here in green. And we see that the slope of the tangent line and the slope of the secant line are way different. Okay, those two slopes are not the same. But when we take the limit as h goes to 0, okay, so as this h value here goes to 0, that's going to move this point. It's going to move this point here really close to the point in green. Okay, so if we move that point really close to the point in green and I draw the secant line passing through those 2 points, the secant line does in fact become the tangent line. Okay, so again, if we move the 2 points really close together, the slope of the secant line is the slope of the tangent line. Okay, so that's how we go about calculating the slope of the tangent line for right now. Okay, now when it comes to finding instantaneous rate of change, we only need 1 point to find the instantaneous rate of change. Like we said before, if we're calculating average rate of change, we need 2 points on an interval to calculate average rate of change. Okay, so let's get into some examples here involving calculating average rate of change and instantaneous rate of change. All right, so directions for the first say to consider the function f of x equal to x squared. And question number 1 asks, what is the average rate of change on the closed interval from 2 to 4? Okay, so if we want to calculate average rate of change, that is going to be equal to the slope of the secant line, which is going to be equal to f's value at the endpoint 4 minus f's value at the starting point 2 over the length of our interval, which is 4 minus 2. So again, that's rise over run. That's a change in the y direction over the change in the x direction. So if we want to calculate f's value at 4 and 2, we're just going to plug those values into our function here. Okay, so f's value at 4 squared is 16, minus f's value at 2, 2 squared is equal to 4, all over 2. So that's 12 divided by 2, so the slope of the secant line there is going to be equal to 6. Okay, question number 2 asks, what is the instantaneous rate of change at x is equal to 2? Okay, so what I'm going to do for this, I'm going to work this out both ways, okay, using these two limit definitions from above. Okay, so I'm going to do the one on the left first. So the instantaneous rate of change at x is equal to 2, the slope of the tangent line, which is going to be equal to f prime of 2, is going to be equal to the limit as x approaches 2 of the function f of x minus f of 2 all over x minus 2. Okay, so this is going to be equal to the limit as x approaches 2. F of x is x squared minus f of 2, that's 4, all over x minus 2. Okay, if we try using direct substitution, we get something of the form 0 over 0, which is always going to be the case for us when finding the instantaneous rate of change. So if we get something of the form 0 over 0, again, that means we can use one of our 3 techniques, either factoring, multiplying by a conjugate, or simplifying. And I think factoring works the best here. So that's numerator is going to factor to x minus 2 times x plus 2 over our denominator x minus 2. And once we eliminate that, we can use direct substitution, and we get 2 plus 2, which is going to be equal to 4. So that makes the slope of the tangent line, which is equal to f prime of 2. That's going to be equal to 4. Okay, now, again, I don't like using this technique. And the reason I don't like using this technique is if your function was like x cubed minus x minus 4, you would get a numerator that looks something like this. And factoring that numerator in this particular case would not be good, because you'd have to use Descartes' rule of signs and the rational zeros theorem, and then guess using synthetic division, and that process is a nightmare for this. Okay, so I don't like using this first limit definition personally, unless it's a certain type of problem which is going to deal with absolute value functions, and we'll take a look at that later on in this lesson. Okay, I like using the second limit definition, but I'm actually going to modify it. Okay, so what I'm going to do instead is I'm going to make this look like something that we worked with earlier in the school year. I'm going to make it look like the difference quotient. Okay, so I'm going to take the limit as h approaches 0 of f of x plus h minus f of x all over h. And then we'll talk about how to proceed at the very end to calculate f prime of a. Okay, what this is going to give me is f prime of x. Okay, all right, so if I'm going to do it this way, and this is how I'm going to do like all of the subsequent examples, because I like this technique here better. Okay, so the slope of the tangent line, which is going to be f prime of x, that's going to be the limit as h goes to 0 of f of x plus h minus f of x all over h. Okay, so this becomes the limit as h goes to 0, f of x plus h means we plug in x plus h wherever we see an x in our function f. So that's going to be x plus h quantity squared minus f of x, which is x squared all over h. Okay, now again, if I try using direct substitution here, we get x squared minus x squared, which is 0, all over 0, which again, I can't evaluate that limit the way that it's written right now. So I'm going to simplify the numerator here. Okay, so when I expand out x plus h squared, we get x squared plus 2xh plus h squared minus x squared all over h. And we can get rid of those x squared terms. So this becomes the limit as h goes to 0. And when using the difference quotient, we should always be able to factor an h out of our numerator. Okay, so when I do so, that leaves me with 2x plus h all over h. So I can cancel that factor of h. And when I cancel that factor of h, that leaves me with 2x plus h, and I can use direct substitution. When I plug 0 in the place of h, that's going to make that limit equal to 2x. Okay, so what does that mean? That means that f prime of x is equal to 2x. Okay, so what this gives me, this is going to give me the slope at any point x. Okay, so we are trying to calculate the slope of our graph, or the instantaneous rate of change at x is equal to 2. So what I want to do is I want to evaluate that derivative at x is equal to 2, which is going to be 2 times 2, which makes f prime of 2 equal to 4. And the beautiful thing about the derivative is when you have your function x squared, which graphically looks like this, what the derivative is going to calculate is it calculates the slope of our graph at any point. So if I want to calculate the slope of the graph at like x is equal to 0, that graph has a horizontal tangent. It has a slope of 0 at x is equal to 0. If I want to calculate the slope of the graph at 1, I would just plug 1 into that function. So the slope at 1, the tangent line at 1 would be equal to 2. The slope of the tangent line at 2 is equal to 4. The slope of the tangent line at 3 would be 2 times 3, which is equal to 6. So that derivative calculates the slope of your graph at any point, which is a really cool result. And that's going to be true for any function. Okay, so I think calculus is beautiful in that mathematicians were able to figure out the relationship between a function and its derivative and how the derivative calculates the slope of your graph at any point. Just an amazing finding. Okay, so on to part 3. What is the equation of the line tangent to f at x is equal to 2? Well, we need two things for the tangent line equation. The first thing we need is the slope of the tangent line. And we already calculated the slope of the tangent line at 2, that's f prime of 2, to be equal to 4. The other thing that we need for our tangent line equation is the point of tangency, which is the point that our tangent line passes through. Okay, so we know that the x value on our curve is x is equal to 2. I want to find the y value on our curve at that point. So we're just going to plug 2 into the original function to get the y coordinate at that point. And 2 squared gives us 4. And then once we have the point and slope, we're just going to plug that into our point slope formula, which is y minus the y coordinate 4 equal to the slope 4 times x minus the x coordinate 2. And when you guys are doing calculus, I want you to leave your equations of the line in point slope form. I do not want them in slope intercept form. So leave them in point slope form. Okay, so let's move on to the next example. Next example says to find the equation of the line tangent to the curve y is equal to 2x cubed minus 5x at x is equal to -1. Now, like this problem is not laid out like the previous one was. Okay, so we know that to find the equation of the tangent line, there are two things that we have to determine. Okay, number one is the slope of the tangent line, okay, which is asking us to find the instantaneous rate of change or the derivative of our function at x is equal to -1. Okay, so we know we have to find f prime of -1. That's going to be the slope of the tangent line. And the second thing we need to determine for the equation of the tangent line is our point of tangency. Okay, so we know the x coordinate of our point is -1, and then we're going to plug -1 into our function to get the y coordinate of our point, which is going to be 2 times -1 cubed minus 5 times -1, which is going to be -2 plus 5, which is going to make the y coordinate 3. Okay, so we're going to need this after we determine the derivative. Okay, so we want to find the slope of the tangent line, which is the derivative. So the slope of the tangent line, which is equal to f prime of, I'm going to do f prime of x first, and then I'm going to use that to calculate f prime of 1. Okay, so f prime of x is going to be the limit as h goes to 0 of f of x plus h minus f of x all over h. Okay, which is the limit as h goes to 0. So f of x plus h will be 2 times x plus h cubed minus 5 times x plus h minus, we have to subtract the entire function f of x. So that's going to be 2x cubed minus 5x all over h. Okay, so I'm going to expand this out. Again, I can't use direct substitution here because if I plug 0 in the place of h, the numerator becomes 0 and the denominator is 0. But I'll be able to simplify the numerator and then factor an h out that we can cancel with that factor of h on bottom. Again, you guys have a lot of practice with that back in chapter 1 in this class. Okay, so this is going to become 2 times x plus h cubed. If I use the binomial theorem for that, that's going to be x cubed plus 3x squared h plus 3xh squared plus h cubed When I distribute negative 5 across both terms, I get negative 5x minus 5h. And then I'm going to distribute negative 1 across the next two terms, so that's minus 2x cubed plus 5x all over h. So this becomes the limit as h goes to 0 of 2x cubed plus 6x squared h plus 6xh squared plus 2h cubed minus 5x minus 5h minus 2x cubed plus 5x all over h. Okay, so the terms that we can get rid of, the positive 2x cubed and the negative 2x cubed, the negative 5x and the positive 5x. And when I look at what's left over, I can factor in h out of the numerator. So when I factor in h out of the remaining terms, we get 6x squared plus 6xh plus 2h squared minus 5 all over h. And then once we eliminate that factor of h, now we can use direct substitution. So when I plug 0 in the place of h, that term goes to 0 and that term goes to 0. Okay, which leaves, sorry, I ran out of space here, so I'm going to continue over here. That's going to make f prime of x then be equal to 6x squared minus 5. Okay, now we want to calculate the slope of our graph at negative 1. So f prime of negative 1. When I plug negative 1 in the place of x, that's negative 1 squared, which is 1 times 6, which is 6 minus 5. That makes f prime of 1 equal to 1. And that's the slope of my tangent line. And then we have the point negative 1, 3 that our tangent line passes through. And then once we have the slope and point, we can plug that into our point slope formula, which is y minus the y coordinate of our point 3 equal to the slope 1 times x minus negative 1. X minus negative 1 is the same thing as x plus 1. Okay, so that right there is our tangent line equation. All right, let's continue on. So we're going to define something new now. Okay, so the line normal to a curve at a point is the line perpendicular to the tangent line at the point of tangency. Okay, so again, the line normal to a curve at a point is the line perpendicular to the tangent line at the point of tangency. Hold on one second, guys. What, honey? Okay, sorry. I have to watch my son right now. So the line normal to a curve at a point is the line perpendicular to the tangent line at the point of tangency. Okay, so if we ask the question, okay, so if we ask the question, what is the equation of the line normal to the curve? In the previous example, at the point specified in that example, okay, the slope of the normal line is going to be perpendicular to the tangent line. Okay, so we know that perpendicular lines, there are two ways that you can define their slopes. The first way is you can say that the product of their slopes has to be equal to -1. The second way that you can describe the slopes of perpendicular lines is to say that their slopes are negative reciprocals of one another. Okay, so if the tangent line has a slope that is +1, the negative reciprocal of +1 is -1. So the slope of the normal line is going to be -1. And then the point of tangency is exactly the same as the previous example. That is the ordered pair -1, 3. Okay, so if we want to find the equation of the normal line here, that's going to be y minus 3 equal to the slope of the normal line, which is -1, times x minus -1, which is x plus 1. So this right here would be the equation of the normal line in that particular example. Okay, so we're going to do 2 more examples and then we'll wrap up the first part of this video. Okay, so the next question asks, what is the equation of the line tangent to f of x equal to 3 over x at x is equal to 3? So again, the two things that we need for the tangent line equation are the slope of the tangent line, which is going to be f prime of 3 in this case. And then we also need the point of tangency. So the point of tangency, the x-coordinate of that point is 3. And the y-coordinate of that point, when we plug 3 into the function, the y-coordinate of the point is 1. Okay, so we want to find the slope of the tangent line. Okay, so we want to calculate f prime of x, which is going to be the limit as h goes to 0 of f of x plus h. So I'm not going to write this out here. I'm not going to write out the step f of x plus h minus f of x all over h. So I'm just going to write f of x plus h, which is 3 over x plus h, minus the function f of x, which is 3 over x, all over h. Again, I can't use direct substitution with this because if I try, I get something of the form 0 over 0. Okay, so I just want to be able to simplify this where I can evaluate the limit. So for me to do so, I'm going to multiply the top and bottom by the common denominator of the smaller fraction. Okay, so this here is going to become the limit as h goes to 0. When I multiply x times x plus h by the first fraction, the x plus h's cancel, which leaves me with 3x, minus, when I multiply x times x plus h times the second fraction, we get 3 times the quantity x plus h. And then on bottom, we get x times h times x plus h. Okay, so the numerator here, we get the limit as h goes to 0 of 3x. And then when I distribute -3 across both of those terms, we get minus 3x minus 3h over x times h times x plus h. So we see that the 3x and -3x cancel. And then I can cancel this factor of h on top with the factor of h on bottom. So this is going to become then the limit as h goes to 0 of -3 over x times x plus h. When I plug 0 in the place of h now, we get -3 over x squared. Okay, so we want to evaluate this derivative here at x is equal to 3. So when I plug 3 in the place of x, we get negative 3 over 9, which is negative 1/3. So that's the slope of our tangent line. And then our point of tangency is the ordered pair 3, 1. And then when I plug that into my point slope formula, it's y minus the y coordinate 1 equal to the slope, negative 1/3, times x minus the x coordinate 3. Okay, and that right there is your tangent line equation. Now, I know the question doesn't ask you for this, but let's just practice with it nonetheless. Okay, let's say the problem wanted us to find the equation of the normal line. So if we wanted to find the normal line equation, the only thing that would change for the normal line equation would be the slope of the normal line. So if the normal line is perpendicular to the tangent line at the point of tangency, the normal line is going to have a slope that is the negative reciprocal of the tangent line. So the negative reciprocal of negative 1/3 is 3. The point of tangency is the ordered pair 3, 1. So our equation for our normal line would be y minus 1 equal to 3 times the quantity x minus 3. Okay, so that would be our normal line equation in blue. Sorry for the noises in the background, guys. This is COVID-19 life for me. So, okay. So one more example, and then we'll finish off part 1 of the lesson. And there are 2 more parts to go, so that tells you how long this lesson is going to be. Okay, so directions here ask us to find the equation of the line normal to f of x equal to x minus 2 over x minus 3 at x is equal to 4. Okay, so the 2 things that we need to determine, again, are the point of tangency. So we can figure that out really quick by plugging 4 into our function. So 4 minus 2 makes the numerator 2, 4 minus 3 makes the denominator 1, and 2 divided by 1 is 2. Okay, and then we're also going to need the slope of our normal line at x is equal to 4. To find the slope of the normal line, we're going to need to determine the slope of the tangent line first. Okay, so to get the slope of the tangent line, we need to calculate what f prime of 4 is going to be. And then the slope of the normal line is going to be the negative reciprocal of that. So that's going to be negative 1 over f prime of 4. Okay, so I'm going to calculate f prime of x here. So this is going to be the limit as h goes to 0 of f of x plus h. So again, I'm going to plug in x plus h wherever I see an x. So that's going to make x plus h minus 2 over x plus h minus 3 minus f of x, which is x minus 2 over x minus 3 all over h. And just like we did in the excuse me, in the previous example, I want to multiply the numerator and denominator by the denominator of the common denominator of the smaller fractions, okay, which is x plus h minus 3 times x minus 3. I'm almost done, son. Okay, so this is going to make f prime of x equal to the limit as h goes to 0. When I multiply that product times the first fraction, the x plus h minus 3's cancel. So that gives me x plus h minus 2 times x minus 3 minus. When I multiply that product times the second fraction, the x minus 3's cancel. So that leaves me with x minus 2 times x plus h minus 3. And then I'm going to leave that denominator in factored form. Okay, so I'm going to need to multiply out that numerator. Papa. Come on, Papa, I'm almost done. Okay. So f prime of h is going to be the limit as h goes to 0. So I'm going to distribute x across all three terms and then negative 3 across all three terms. So when I distribute x, we get x squared plus xh minus 2x. And then when I distribute negative 3, we get negative 3x minus 3h plus 6 minus, and then I have to subtract the entire quantity whenever I multiply out those next two polynomials. Okay, so when I distribute x across all three terms, we get x squared plus xh minus 3x. And then when I distribute negative 2 across all three terms, we get minus 2x minus 2h plus 6. All over my denominator. Okay, so we get h times x plus h minus 3 times x minus 3. Okay, so I'm going to try to simplify this as easily as I can. So we have x squared minus x squared, so those terms cancel. We have xh minus xh, so those terms cancel. We have negative 2x minus negative 2x, so those terms cancel. We have negative 3x minus negative 3x, so those terms cancel. And then we have 6 minus 6, so those terms cancel. So all we're left with on top is negative 3h minus negative 2h, which makes that numerator negative h. So we get f prime of x equal to the limit as h goes to 0 of negative h over that denominator. And then once we eliminate that factor of h, now we can use direct substitution. So when I plug 0 in the place of h, this is going to wind up becoming negative 1 over x minus 3 squared. Okay, so that's what f prime is equal to. F prime of x is negative 1 over x minus 3 squared. Now, we want to evaluate that derivative at 4. Okay, so f prime of 4 is going to be negative 1 over 4 minus 3 squared, which is negative 1 divided by 1, which is negative 1. So that's the slope of our tangent line. We want to find the normal line equation, so we have to calculate the slope of the normal line. So the slope of the normal line is going to be the negative reciprocal of the tangent line. So the negative reciprocal of negative 1 is 1. And then our point of tangency is the point 4, 2. So once we have slope and point, we can plug that into our point slope formula, which is y minus the y coordinate 2 equal to the slope 1 times x minus the x coordinate 4. All right, and that right there is our normal line equation. Okay, so again, that takes us through the first third of our lesson, and then we'll work through the next 2/3 in the next 2 videos.